Hello, this is Eric from UNC Charlotte, and today we'll talk about caching on multicore system. We talked before about caching in the context of a single core system. We'll talk today about what happens when we have multiple caches in the system, multiple cores, multiple processors. So what usually happens whenever we have a multi-core system is that some of the layers of cache are actually dedicated for each core, and some of them are shared between all the cores inside of a processor. In this particular case here, which I think comes from an Intel system, you have caches that are specialized for each core at level 1 and level 2. But the level 3 level of cache is actually shared among all the cores. And this is actually an opportunity in architectural terms. It means that the cores can actually share data without having to go to memory because they actually share a common level of cache. Now, it does pose challenges because whenever we are programming it, we might get confused about how much cache we already have. For instance, if we have 8 megabytes of L3 cache and each core works on its own part of the data, then each core doesn't actually have 8 megabytes available to it, it only has 2. On the other hand, if all the cores are actually working together on a single piece of data, then they can actually work on 8 megabytes at once because the data is going to be shared inside the L3 cache. Now, the question that we have to ask ourselves is how does this sharing actually happen in practice? And we will see that the details of how this sharing happens is going to impact performance. At the level of the cache, what happens is that there is a cache coherency protocol to make sure that the different caches for the different cores are actually coherent between each other. And the name of the most classic protocol is MESI, M-E-S-I. And the name of that protocol is a stand-in for the different state that each cache line can be in the cache. So inside of the cache, each cache line can be in one of 4 states. It can be in the M state, the E state, the S state, and the I state. If a cache line is in state M, that means that it is in modified state. That means that the value that is stored in the cache is different than the value that is stored in memory because the data has changed, but that data has not been pushed back to memory yet. That means that at some point, write back will need to happen. If the cache is in E state, it means that it is in exclusive state. What that means is that the cache is currently coherent with the memory, and this cache is the only cache which actually holds the data. If the cache is in the shared state, it means that the cache holds a cache line that is coherent with memory, but there are other caches in the system that may store that particular line of cache. And finally, the cache may be in invalid state if the cache holds a cache line that is not coherent with memory, but that is also wrong. The memory has the correct value and the cache has the wrong value. What will happen is that depending on what type of event is happening on that cache line, then the state of that cache line is going to go from one state to the other state. If we are in modified state, that means that the data that is stored in that cache line is not committed to memory, but it is actually the correct value, and write back must happen. What the cache is going to do is that it is going to snoop on the memory bus, on the cache bus, in order to see what other accesses to this cache line may be happening. And if another cache tries to read that data from memory, that particular address that is stored in the cache line from memory, the cache that is in modified states knows that the memory doesn't hold the correct value. So what the cache is going to do is that it will request the other cache to back off so that it has time to write the data back to memory. And once it has done that, it will change its own state to shared because it knows that another cache is about to read that piece of data. Finally, it is possible that the cache will need to be flushed. For instance, if the line needs to be evicted or something like this, in which case the line can always go back to invalid after being pushed back to memory. If the cache line is in exclusive state, it means that this cache is the only cache to store this particular line, and the cache line is actually coherent with whatever is being stored in memory. What that means is that if the core requests to write on this particular cache line, then the cache line will go to modified state, because at that point it will no longer be coherent with memory. The cache is also going to snoop on the memory bus, so that if an other cache tries to read the same cache line, then the cache will no longer be exclusive, it will be shared, so it will change its state to shared. If the cache line is in shared state, It means that multiple caches may store this particular line. And in terms of accesses, what happens is that if the core writes onto this particular cache line, then the only way it can do that is by first invalidating the cache line from other caches so that it can be the only one to actually have the correct value, and then it will go to modified state. Finally, if the cache is in invalid state, that means that the cache line is incoherent with the value that is in memory, but the value that is in memory is the correct one, and the value that is in cache is incorrect. And whenever the data is being read by the core, the cache will go either to exclusive state or shared state, depending on whether another cache has that piece of data in its own cache. It's actually important to understand how the cache works. The cache, because of that state management that it needs to do, the cache may actually take some time before it can actually do the operation that the core would like it to do because of that cache coherency protocol. The cache line may not be available immediately, it may not be written back immediately. So whenever the core makes any memory access to the particular cache, it doesn't happen immediately. It enters a buffer called the write buffer that at some point will be taken into account. And that buffer is actually chopped in blocks of 32 bits typically. And so what that means is that if you're trying to do an access that is smaller than 32 bits, you will need to pad it to 32. And if you're trying to make an access that is bigger than 32 bits, then most likely you will have to chop it into chunks of 32 bits. Also, the cache will only be able to write data onto a particular memory location if it actually has the entire cache line available to it. And what that means is that before you can actually write any piece of data, the data needs to be available in the cache itself. And the name of that principle is read for ownership. And what that means is that if you're trying to account for how much transfer is happening on your memory bus, you need to account that even if you're only writing to a particular location, you will need to read from it first. And this causes delays because the cache needs to be resolved. Let's think through a few scenarios and try to see if we can figure out what all these behavior of cache actually mean. Let's imagine that we have an array A, it's an array of characters, so characters are bytes, and all the threads in our system are going to run something like this. A of thread ID equals to 1. What do you think is going to happen whenever we do this? I suggest you pause the video here and think about what could possibly happen. And once you have an idea, then get back to the video. What will happen in a case like this is that it is possible that not all values inside the array A will actually be set to 1 at the end. And the reason for that is because all write operations are actually performed by 32 bits. But characters are actually 8-bit wide. That means that whenever we're trying to write 1 to a particular byte in memory, the processor actually needs to read 32 bytes, replace one of these bytes, and write it back. And if two threads try to write on the same 32-bit segment at once, it is possible that the output that we will get will be incoherent. Something else that can happen to us is in a scenario like this. Here we have an array of integers, and all the threads are going to execute this particular code. They're going to loop from 0 to 10,000, and they will try to write that particular value to an array indexed by their particular thread. Pause the video for a second and think about what that may actually do. What may happen in this case is a phenomenon that we call force sharing. And the idea is that there will be no data loss because all the writes are happening by 32 bits because these are integers. However, there is going to be a performance issue. What you will have is that you are going to have multiple threads writing on the same cache line, even though they're writing on different 32-bit segments than one another, they may still be writing on the same cache line. And when that happens, the only way we can write on the cache line is if our cache actually holds that particular line in the exclusive state or in a modified state. But if you have two cores that are actually trying to write to the same cache line, then they will actually fight back and forth to get the cache line exclusively to themselves so that they can write. And this will cause extraordinary traffic on the memory bus, and that will cause a lot of latency in the system. So this phenomenon is often referred to as force sharing, and it is typically the reason why on all pieces of data that you have that is not performance critical and that you don't have a whole lot of, if you're going to do accesses that are indexed by the number of threads that you have or something like this, usually we'll pad it so that that information sits on different cache line. All right, let's think about what will happen if we have a bunch of threads who are all doing accesses like this, a of 0 plus plus. Once again, feel free to pause the video and think about it. When we have this kind of access, we might have a race condition happening. The idea is that it's possible that one of the core is going to read the value of A0, and after that happens, another core is going to read the value of A0, increment it by 1, and write it back. So whenever the first core is going to do its own increment and write back, it will not take into account the operations that have happened on another core. In order to solve this, there are multiple atomic operations that are actually provided by the architecture to help this kind of behavior. They're usually called fetch and add and fetch. The idea of these operations is that they're actually atomic operations that are encoded within the memory subsystem and that enable you to do these transactions atomically. You will atomically be able to read a memory location, add one, and write it back. The way these instructions are usually implemented is that the memory controller is going to lock a particular cache line to make sure that no other core can actually read it. And this is actually expensive because it means that you need to monitor the particular memory bus, and if that cache line is being requested, you need to post some backoff mechanism until the write back has happened. Another common use case for atomics is to perform compare and swap. Here we have a code that will read the value of A0, and if it has a particular value, it's going to change its value and write, for instance, 12 in it. Pause the video if you want to think about what can go wrong here. Here again, the problem that you have is that there is a data race. It is possible that you read A0, and by the time you test it, another core has come and actually has changed the underlying value of A0, and because of that, whenever you make the decision to write to 12, the value of A0 has actually changed in memory sense, and you were not aware of that. There are instructions here that can help you as well. They work in a similar way, and they provide compare and swap operation that will do both the comparison and the write, if there need to be a write, atomically by making sure that the particular cache line is being locked in memory. More generally, there are other locking mechanisms that can be used. The function test and set atomically will write 1 to a memory location if the value is currently 0. And this particular atomic operation is actually used in order to implement spin locks, which are a variant of mutexes. And the reason why people like spin locks instead of mutexes is because spin locks happen in user space instead of happening in kernel space, so you don't need to context switch inside the kernel to be able to use spin locks. And the idea of how the lock works is that you will be able to take the lock by essentially looping over that test and set operation as long as you haven't actually set the lock yourself. And whenever you have taken the lock, at some point you can unlock it simply by writing to memory. One of the reasons why people do not like these spin locks, at least when they're implemented like this, is because they are going to saturate the memory bus. Because as long as you don't have access to the bus, you're going to keep pulling with atomics in order to make access to it. And since those atomics are going to lock the cache line, it can become difficult for the thread that will want to unlock that particular cache line to do so, because it can't actually get write access to it. So in practice, spin locks are not directly implemented like this. They tend to be implemented with a version that is like this, that is going to loop infinitely until the particular memory location has been unlocked, and only when it has been unlocked, then it will attempt to set it atomically. This is better because it does not lock the memory bus. Actually, as long as you have the correct value for star lock inside of your cache, then it will not do memory transactions on the shared buses. And so that means that simply by monitoring the whether that cache line has been written or not, then this algorithm is going to perform correctly without actually saturating the memory bus. In conclusion, for multi-core programming, the thing that we need to remember is that caches, at least at some level, are being shared, and that's both a blessing and a curse, because we get access to more amount of caches, we have a bigger cache, we can communicate using the cache, but we also have all these cache sharing issues that appear. And in particular, we need to pay attention to fault sharing, cache invalidation, and atomicity whenever we program these multi-core system. In terms of performance, what we need to worry about is fault sharing and read for ownership, which tend to be the most problematic, the most uncommon behavior of these systems. And we need to remember how atomics work, because they are powerful in the sense they enable us to program complicated things, but they're also expensive at the same time, so we need to use them sparingly. All right, that's how caches and memory works on a multi-core system. But how does it work on a multiprocessor system? Well, usually it's going to look a little bit like this. Here is a picture of an old Intel system where you have 4 processors. Each of these processors has some number of cores in there. And one of the benefits that you have whenever you have more processors is that you have more memory controller. Here, each processor has 4 memory controller. Since you have more memory controllers, you're going to have a higher bandwidth overall together between all the processors. Now, part of the problem is that since some of these memory chips are connected to one processor and not to the other processor, if this particular down left processor wants to access the memory of the top left processor, then it will have to do that through a particular bus, which used to be called QPI for Intel processors, in order to be able to access that memory. And what that means is that now the memory that is stored here on the bottom left is actually closer to this processor than the memory that is connected at the top left. And what it means is that if the bottom left processor tries to access the memory of the top left processor, it will see a lower bandwidth and a higher latency. And this is why this type of architecture are often called non-uniform memory architecture, often called NUMA architectures, because now not all processor has access to all the memory in the same way. They have to go through these special QPI buses. A QPI link is typically as fast as a single memory controller. So it's not very slow to go through QPI, but it is usually slower than the aggregated bandwidth that you will see out of your architecture. And that means that if all the memory of your application happen to all be stored on a particular processor, then the other processor will only see a fraction of the bandwidth that you would expect. So the placement of memory on the different memory devices is actually going to be important. It means that you're going to care about where your memory is located. And the most typical way of handling this is to use simply automatic memory allocators, and you can actually control them and choose what they are. And the idea is that most systems have 4 different allocation policies for memory. Memory is always allocated per page, and the default policies is one of these 4 policies. The first one is to allocate the memory on the processor that's called malloc to allocate it. The second policy is to interleave memory on all nodes regardless of what happens. So if you have 4 processors, all pages that are 0 mod 4 will go on processor 0, all pages that are equal to 1 mod 4 are going to go on processor 1, etc. The third policy is to allocate all the memory on one particular node. And the last policy, which is usually the default policy, is the first touch policy. And what it does is that it will allocate the memory to the processor that allocates it first. The first processor to touch a page is going to be the processor where that page is going to be allocated. That allocation policy is usually considered reasonably smart for most applications, because if you have data that is going to be shared across all your processors, very often that initialization is going to be done in parallel itself, which means that the different pages of your shared data is going to be spread across your different processors. On the other end, the data that is proper to a particular core or processor of your system is going to be allocated near to that processor. So all the bookkeeping data is going to be closed, and all the shared data is going to be distributed across your system. which is often the best strategy that you can have. If you know a lot about your application and about your architecture, you can actually control memory allocation manually. There is a library called libnuma that will let you change allocation policy, allocate memory explicitly on a particular node, and move data from one processor to another one. These NUMA effects, I've been talking about them, but do they actually matter? Are they actually important for performance? And the answer is yes, they're important. They're not the most important aspect of your architecture, but you probably should not completely ignore them. Here are the performance of an application that I wrote a few years ago, which is going to hit memory in different ways. It's a multi-machine application. That's why you have working node on the x-axis and performance in updates per second on the y-axis. The ins and outs of the application doesn't matter, but ideally you would want to have higher updates per second as you can. What you can see is that if you're allocating only a single thread per node, if you're using only a single core, then we're getting about 1500 updates per second. If we are using 4 thread on that architecture, we're getting about 5500 updates per second. And whenever we allocate the 8th thread on each of the nodes, the performance is going to differ depending on our allocation policy. If we're allocating it so that there is only one graph per thread, or one graph in total, we're getting about 10,000 updates per second. But if we allocate one graph per NUMA node in the architecture, then we can actually gain about 10% of performance and reach 11,000 updates per second. So whenever you are running application on a multi-core and multiprocessor system, what you need to remember is that all synchronization are going to be slower on multiprocessor because memory is further away. The memory is going to be distributed to multiple memory banks attached to the different processors usually. And what that means is that not all memory banks are going to be easy to access by each core of your system. It means that you will experience reduced latency, reduced bandwidth, and increased latency for most memory accesses. Even though you can control the memory allocation of data one page at a time, usually the best policy is still to let the first touch policy handle the allocation and allocate the data close to the processor that touches the data first. And that's actually all I wanted to say about memory allocation in multi-core and multiprocessor systems. Have a good day.